Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
For me to welcome Marta Kwiatkowska from the University of Birmingham. Marta is here on several occasions, I guess. I think the main one is a systems biology seminar that's going on in Seattle. Marta is a pioneer in probabilistic model checking and is not only working on systems biology but also on computer systems, and that's what she's going to talk about here today. Thank you.
Thank you. Thanks for coming. So as Jakob said, I'm going to talk about probabilistic model checking. But this morning I gave a talk at the Institute for Systems Biology, and I was talking about applications of probabilistic model checking to biological processes. But today I'm going to talk about analyzing mobile ad hoc network protocols with probabilistic model checking. Now, probabilistic model checking is a research program that I've been working on for about 7 years. I'm not saying it's just me. I've been working with lots of other people. You'll probably see their names towards the end. And this has resulted in a software tool which we call PRISM. And all the examples that I'm going to mention have been modeled and analyzed with PRISM. So what is the talk going to be about? Well, first of all, mobile ad hoc network protocols and why we might want to verify them, what probabilistic model checking is, what it involves. I'll say a little bit about the PRISM model checker, and I'll mention some case studies. I've got 4 in the talk, but I'll see how we get on, and I might need to skip some of those. And I'll finish up with some challenges for future. Right, ubiquitous computing. The trends in ubiquitous computing. Well, the devices are getting ever smaller, even so smaller that they are becoming mote-sized. This is an example of a crossbow mote device. It's supposed to be 1 millimeter cubed. It's not at that size yet. It is about 1 inch cubed. Networking, of course, is increasingly wireless and global. And what that means for systems and system software is that it has to become decentralized, self-organizing, self-configuring, autonomous, adaptive, and context-aware. So that's what the systems are increasingly going to look like. But at the other side, we have users, and we know that users expect assurances of safety, correctness, but also performance and reliability. And for example, if you are using an e-savings account, then you want to know whether your account is secure. Can someone blue snarf from my phone? Have you heard about blue snarfing? This is a phenomenon through which, by a loophole, it is possible to steal the contents of your phone book from a Bluetooth phone without the owners knowing. And also how fast the communications are, energy efficiency, etc., etc. And these are, with the exception of blue snarfing, these are the questions that we've been working with as part of the probabilistic model checking research program. This is because it turns out that in this ubiquitous decentralized computing scenario, probability helps. How does it help? Well, in for example, in distributed coordination protocols, it is well known that in the presence of failures, there are no symmetric solutions to certain coordination protocols. But these solutions exist if you admit randomization. What you have to weaken then is the property of resolving the coordination. In this case, the leader election is eventually resolved with probability 1 as opposed to always. Yeah?
So I have two questions. One is what does symmetry mean, and what does eventually range over?
Right, okay, so this symmetry means that every node in the network is running the same protocol.
All right.
And eventually is unbounded.
What's the parameter that's unbounded? Is it as
It's
time goes?
Well, you can count time. Yes, you can count time steps. You can count path lengths. So it depends on with which model you are working.
But you're running a different algorithm. You're not running the standard leader election algorithm over and over again. You're doing more than that.
Well, I'll show you right at the end. I'll show you a genuine example of a randomized leader election algorithm.
Okay.
So I think you'll be able to, yeah. Gossip-based routing is another example where instead of using flooding, which is very expensive, you might send messages with some probability to a subset, and this way reduce the network utilization. Now, probability is also useful when modeling uncertainty in the environment. Probability is very useful to quantify failures, for example, and to express properties known as soft deadlines. As opposed to hard deadlines, these are deadlines that can be missed, but you might want to quantify how frequently they are missed or not. And also to quantify environmental factors and for decision support in AI. And finally, when analyzing system performance, as is well known and has already been used since probably 1910 or so. So here are some examples of real-world protocols which actually use randomization of a different kinds. Randomized backup schemes is something that sort of started off with the Ethernet, but is also present in the Wi-Fi protocol, in the Bluetooth protocol, which I hope to come back to. There is an anonymity protocol called Crowds, which uses randomization, and that's randomization of a choice of routes. This is an example of a randomized leader election protocol, which is running in the actual FireWire protocol, 1394 FireWire protocol, and the Zeroconf IPv4 dynamic configuration protocol, and there are more. And these are just examples which only use discrete probability and timing delays. But in order to model traffic delays, for example, you need continuous probability distributions. I have not mentioned that, but these can also be modeled and analyzed. So, of course, what we want to do is we want to bring in verification. Now, verification conventionally is a program, okay? I'm picturing here a machine. The idea is that this is completely automatic. You just turn the handle, and this machine is known as a model checker. So it inputs a graph representation of your program or whatever other model. It also inputs a temporal logic property, and then it can output either check, yes, this property holds, or not, it doesn't, and you can also get an error trace, a trace to error, which you can then take back to the designers and try to convince them that it doesn't work. So this is conventional model checking. Now, probabilistic model checking is a machine similar to the one before, which I now call a probabilistic model checker. It inputs a probabilistic model, and this is a graph where paths through that graph, executions, are chosen according to some probabilities. So, for example, coin tossing, or perhaps even rates in the sense of exponential probability distributions. So this is a probabilistic model, and what we also input is a probabilistic temporal logic specification. Now, what this one is saying here is, in contrast to the previous one, there is an operator here called a probabilistic quantifier, and what that probabilistic quantifier will allow us to do is to calculate the probability of all paths that satisfy what's in the brackets. So basically what this property is saying, that whenever I send something, then the probability of this thing being eventually delivered is at least 0.9.
Martha, I have a question.
Yeah.
In a few slides earlier, you showed various examples of models that use randomization or probability.
Yeah.
In your experience, is it the case that whenever a coin is flipped there, you usually just, it's like a uniform distribution? So all the edges from a certain state are taken with equal probability, or sometimes you've seen very skewed things?
It does not have to be a uniform distribution. So there are cases I'll show you actually in the leader election, it is just simply an electronic coin, so it's probability a half and a half. And in Zeroconf, it's a uniform distribution, but in other examples, it's not. For exponential backup, for example, it is not.
I see.
Yeah.
So, go ahead. Another question.
In this picture, what's probabilistic? The cryptic structure, the modalities, the model checking, or all of it?
Okay, so I have to admit that this is an ambiguous name, okay? And this is my fault, entirely my fault. I didn't think of it. That's how I introduced the term in '98 in the first workshop. So probabilistic is linked to the model. So this is a model checker for probabilistic systems, okay? And in this case, as you can see, the model is probabilistic and the specifications are probabilistic. But I can also have non-probabilistic specifications for this probabilistic model. Yeah.
So now, actually, I have another question.
Yeah.
So you can, of course, for a probabilistic model, you can have a specification which says that, let's just talk about safety, reachability of an error.
Yeah.
You could say that, I want it to be the case that no error state is, that if an error state is reached, it's reached with eventually zero probability. So what that probably means is that it is possible to get there, except that it's very rare. So do you
exactly.
Can you have a specification like that?
You can, yes.
So
with probability 1 is not the same as always.
Yes. So now my question is, if you give that kind of a certification to these engineers who work with these systems, are they happy with that, or would they say, no, I don't like this, I want full certification, I don't want safety to be violated in any circumstances?
Perhaps, so you see, safety is probably not a very good example of a property that you want to guarantee via probabilistic model checking.
I see.
Aliveness, soft deadlines, yes, okay? So I'll actually show you some real-world protocols that you might be running on your home network, okay? And the question is, are you happy, you see, with them? Yeah, but safety is not a good example. But yes, it is a crucial observation that something happening with probability 1 is not the same as something happening always. And this is what I meant, that when you switch from distributed coordination to randomized distributed coordination, you actually trade off something. You have a weaker property.
So the high-level bit I take away from your comment is that for safety checking, I just ignore all the probabilities and all the edges.
If it
for
is
liveness checking, I pay attention to them.
Yeah.
All right.
Yeah. I mean, you can also have, sort of invariance with probability, but it is not something on which human life, can depend. However, if you think about safety critical systems, if you think about flying an aircraft, what does it mean that something is absolutely safe? These things do not exist. There is always a non-zero chance that the aircraft will come down. So, but these are very, very important issues that I think one has to realize before using a tool like this. So that's what we input. What we output is the tool will output either yes, this is true, or no, this is not. And you can also trace down a counterexample, but the counterexample is a tree, is not a path. But what's most useful is the probability. And that's what we have learned, say, over the 7 years of experience with PRISM, just extracting probabilities, these quantities. So that's what the probabilistic model checker does. There is quite a lot of probability elsewhere in other areas, and in particular in performance modeling, There are models known as continuous time Markov chains, which have been used, in steady state and transient analysis. In AI and planning, for example, there is another model which is known as Markov decision processes, which is used. Now there, what they want to do is they design algorithms for optimum policies. Now, in probabilistic model checking, the focus is different. What we want to do is we want to develop algorithms for automated verification of these probabilistic systems, for temporal logic-based specifications. However, the models are actually shared with both of these areas. And there has been a crossover of techniques between probabilistic model checking and both of these. I will not have time to talk about that, I'm afraid. Okay? So I'll just give you a little bit of intuition for what's underneath a probabilistic model checker. So the simplest type of model is a discrete time Markov chain. So time proceeds in discrete steps, and I have probabilities here, and these probabilities, I assume they add up to 1. Okay? So basically, if I'm in this state, then what this is saying is that with that probability, I can move to that state. And I only have one probability distribution in each. So graphically, you can think about it as an automaton. And for model checking, we work with finite state automata. They are labeled with atomic propositions in the normal way. And they have these probability distributions here. And some of these are trivial probability distributions. So it's a matrix, state times state matrix, probability matrix. Now, but I need, in order to talk about probability, I need a probability space. So what I do is I unfold the behavior of this automaton into infinite paths, just simply sequences of states, where you just move from state to the next one with positive probability. And you can calculate the probability for finite paths by multiplying these probabilities along. Just for finite paths. For the infinite paths, what I do is I apply a construction which is known as a cone construction. So I take the infinite executions as the sample space. Now, if I take a cone is the set of all infinite executions that have some common finite prefix. Okay? Then I know the probability for that cone. Okay? I know the probability for that cone because that's just the probability of this finite path. Okay? And then it turns out that you can close it to a least sigma algebra. And with that construction, you can now talk about events which are not just like these simple events, okay, where you observe some finite prefix, but you can also observe a disjoint union. You can observe something, with probability 1 unboundedly, as long as you can deconstruct it into a disjoint union of these basic events or basic cones. Okay? So that's the probability construction. Now, what it turns out that for...
in this multiplication, this means that choices are presumed to be independent.
Yes. Yeah. They are.
So just with respect to the previous example that you had, so when you're in state S1, the probability of going to state S2 was completely 1.
Yes.
That wouldn't be an independent event.
That's right. So here, there is only one way of going from S1
to S2.
to S0 to S1.
S0
Yeah,
to S1.
that's right.
Yeah.
There is only one way. Exactly. Yeah. Now, it turns out that discrete time Markov chains are not very good when modeling distributed computation, distributed algorithms. And this is because when you want to combine them in parallel, then in order to stay within the philosophy of discrete time Markov chains, you'd have to multiply the probabilities. Okay? Now, in a distributed system, this does not happen because these the DTMCs might be running on completely independent computers. So what we want is we want a parallel which admits non-determinism. Now, the model that we use for this is actually something that in the terminology, the original terminology by Vardy and Pnueli was called concurrent Markov chains. Okay? So as opposed to discrete time Markov chains, concurrent Markov chains. But it turns out that this model is well known in AI planning as Markov decision processes. So this is why we call this model Markov decision processes. Now the difference is that in this case here, I now have two probability distributions. But there is no probabilistic way to resolve this. Okay, so this is a non-deterministic way to resolve between these two probability distributions. So what I do is I still unfold that into infinite paths, but now I have to code the probability distribution, which takes me from state to state, okay? But I've lost the probability space because, yes?
Oh, I was just wondering, I don't understand where the parallelism is in the picture in this case.
Right, this is a very good point. Okay, so I suppose if I give you an example, imagine that here what I have is that this state is a pair of local states of two DTMCs. One DTMC is just idles, and the other DTMC makes that choice.
All right.
Yeah.
Okay.
So it is not obvious in here. Yeah. But because I have non-determinism, I've lost the probability space. So in order to bring it in, we use a notion of an adversary, which in AI is known as policy and in systems is known as scheduling. Okay? Once you've chosen a particular schedule, which is whenever you are in this state, you have to choose between all the probability distributions to move on, to take next, then you are back down to probability space.
And you're back into one probability
I'm
space.
back to one probability space for each adversary.
Right. So what is the contribution of the non-deterministic choice?
Right, okay. This is how we set up the logic. And this logic was introduced originally by Hanson and Johnson, and it is a variant of the logic CTL. And I mean, those of you familiar with CTL, I assume that everybody here is familiar with CTL, yes, so you should recognize this. What you do not see is for all and there exists. Instead of that, I have this probabilistic quantifier, and you think about it as a quantitative operator. So it's something that gives me the whole range between there exists and for all, okay, with probability. I'll ignore the rest, the costs and rewards, okay?
So is tree structure fundamentally necessary for reasoning about probabilities? I cannot have, would it be conceptually impossible to have a completely trace-based logic with probabilities? What I'm trying to understand here is if the fact that you're using trees has something, I mean, I might imagine that the branching structure of the system, because it's quantified with these probabilities, has to be essentially taken into account, but then I'm wondering, why can't I just, look at the set of all traces of the system and...
I'm sure that there are results. I'm sure Roberto Sengala looked at that. He has some results. But there are two types of, in these models, in MDP models, there are two types of branching. There is the non-deterministic branching where you choose between probability distributions, and then there is the probabilistic branching.
But on the other hand, you're not telling me that it's conceptually impossible to think about...
No, I'm not telling you, and I cannot quote Roberto's results, yes, off the top of my hand, but these questions have been looked at. Yeah. So I'm talking about the specific logic which is based on sort of derivative of CTL, but there are also derivatives of LTL, except that they are more difficult to implement. But people like Moshe Vardi have an objection to this logic for the same reason that people have objections to CTL and branching.
We don't necessarily care about that.
Yeah. Okay. Yeah. So Okay, so this is the semantics. I hope that that answers your question. Okay, so you know what we had is we had these paths, but because we had non-determinism, we had to bring in adversary, and we get, you know, probability space, in fact, a DTMC for every adversary. So the way that this is handled is that I decide that some formula, this formula holds if for all adversaries the probability is in the correct relationship with a bound. So basically when
the adversary controls non-deterministic choices.
The adversary controls non-deterministic choices, and there are results which come back from AI, the MDP results. So this says that under any scheduling, the probability bound is true at state S. And this allows us to reason about worst case and best case scenarios, because in fact what you can get out of model checking is the minimum and maximum probability. You get a whole range. And there are results which say that the simplest adversaries, known as simple adversaries, or stationary policies actually give you the best and the worst case. And anything more complicated is sitting inside the interval. So that's what's happening with the logic PCTL, okay? And I mean, that's the sort of the intuitive, you know, meaning of that. So that's just the summary of. So this was the semantic setup. I've motivated the probability space, okay, but a model check actually has to compute these probabilities. Now it turns out that for DTMCs, in order to calculate the probability of an until formula, there is a linear equation system that can be induced, and that can be induced from the Markov chain representation of that. And this linear equation system has to be solved, whichever way. For Markov decision processes, there is actually a sub-problem of linear optimization problems, which can be solved iteratively. So these are solved typically by iterative methods because the models can be very, very large. And the direct methods are limited, typically up to 1 million states. But with iterative solutions, because you never change the matrix, you can go much, much higher. Now, in terms of the actual model checking, it is a conventional graph traversal with numerical linear algebra and linear optimization. And there is actually more for continuous time Markov chains. But the interesting thing is that for these properties where the threshold is 1 or 0, there is no need to compute the probabilities at all. Because this can be reduced to graph theoretic traversal according to some well-established results, and that's also implemented. And this has the additional advantage that because these methods are iterative, that means we stop computing the probability until convergence, so until the two terms are close enough. And that means that you would never reach 1 comfortably. But with this, we can definitely establish whether something holds with probability 1, which is basically established by a sort of analysis of strongly bottom-connected components. So that's what the model checking is for continuous. There is a whole picture still opening up. There are many models that have not been even attempted. Okay. Now, in practice, okay, what all that means is, okay, so for the models that I've showed you, what I need is matrices which only contain the probabilities. They are not necessarily square matrices for Markov decision processes, because for a Markov decision process, I can have several distributions, several rows for one state. So I can either do it in an enumerative fashion, okay, just work with sparse matrices and model states individually, or symbolically. Okay. And in fact, the latter is the approach that we've taken, and that's what stands for S in PRISM. And the PRISM project is something that I've been working on since about 1998, and has grown into quite a large and quite an international project with quite a few key collaborators who have contributed to case studies, but also to the code and to the theory. Okay. Now what the PRISM tool can do is, well, I've only showed you these two models, okay. But the PRISM tool can also input continuous time Markov chains, and it also has an extension with cost and rewards and expectations. So you can, for example, verify properties such as the power energy consumption, because it can look at quantities, and the expected time until leader election. But there is also another model, which is probabilistic timed automata, for which there is indirect support, but there is also direct support if these automata are a subclass of so-called with digital clocks. Now, PRISM has its own input language, which I'll probably skip over in here, and the implementation uses a symbolic data structure, which is a variant of BDDs. It's called multi-terminal BDDs, and we use directly the CUDG Colorado University decision diagram package of Fabio Somenzi with one or two tweaks. Now, for efficiency reasons, there are three numerical computation engines. The biggest challenge in PRISM was how to combine, in a context of a numerical computation, a symbolic representation of a matrix as an empty BDD with an explicit representation as a vector, because the elements of a matrix stored as an empty BDD are not accessed in the right order. So this has presented us with quite a few challenges, but there are some nice solutions in the papers. So in fact, what we have is we have a symbolic, which is a fully symbolic. Fully symbolic means that the vector, probability vector, is also stored in an empty BDD. Now, empty BDDs suffer from exactly the same problem as BDDs, which is that they depend on regularity. Now, in that case, if that regularity is lost because of the properties of the vector, then the computation just simply explodes. So for that case, there is a hybrid solution, which has an explicit vector, but we also have an enumerative solution, which I think basically it was there just for sanity check and comparison. Now the conclusions really are that no engine wins overall. It depends on the model, depends on the model type. But there are some very large-scale examples. You can, I suppose, go sort of higher with that, with techniques like grid computing and parallelization, but that is not a direction that I would like to move into. I think I would like to use or reuse various abstraction and model reduction methods from conventional model checking and adapt them to this case. So, and these are examples of some real case studies. These are all described on the PRISM webpage if you are interested. And here, they have been classified into the different types of models. I'll probably skip over some of those, but I think I'll just show you the Bluetooth device discovery, and maybe also the IPv4 Zeroconf, because it's an interesting example. Now, okay, so this is also a technicality of PRISM, you see. So what we have learned from experiments that it is very useful in PRISM, instead of specifying the threshold, also say question mark in the case of threshold. And the question then becomes, what is the probability? Okay, what is the probability of that formula? Now, we've also moved further. In this case, I can specify t as a parameter, and I can set up an experiment for PRISM which will range over different values of that parameter. And n is also a model parameter. So in fact, with this experiment, what the model checker will do is it will enumerate all the combinations, and it will construct a model, and for that model run all the possible examples of this, and it will allow you to plot the results. Now, what we also have within the tool is a sort of ongoing development. It's pre-release, I would say, because it's been finished. There is a sampling-based model checking. This is a way to deal with state space explosion by avoiding the need to construct the model. Okay? Instead of constructing the model, you can keep the syntactic representation of the model and use Monte Carlo simulation to create simulation runs and then apply statistical reasoning, for example, to deduce with high confidence that the property is true, just based on the simulation runs. This is what the text editor looks like, and that's what the graphs look like. I've got some more graphs with experiments. And we are also working on this kind of graphical front end. There is the basis of the parallel engine, and we're also working on a grid engine to supplement the tool for, with ways to handle the very large models. Right, so I don't know what you want to hear about. I think the Bluetooth example is something that the audience really likes. So so I'll skip over this example. But I mean, these are all described. I mean, the reason I mention it is that there is an unproven conjecture by Carol Morgan. So if anyone is interested in reasoning about, with probabilistic systems, basically Markov decision processes, and there is something which we can illustrate with the tool, and that is the case 3 is the worst. Okay, seems to be the worst, but we don't know why. There is no theoretical explanation why. Okay, IPv4 and Bluetooth. Okay, right. I mean, I assume that you are all running a network at home, and I assume it is all a wireless network. Yeah. Well, this is a real protocol. Have you heard about the Zeroconf protocol? Yeah. So Zeroconf. Well, I'm told that these people were working at Apple, I think, at some point. So, well, anyway, this study is about the version for IPv4, but there is a version for IPv6. And the idea of that protocol is, just as I was saying, it's instead of running a DHCP server, what you want to do is to provide a means for each device that comes into the network to choose an IP address. But you don't have a centralized node, okay? So that's what it means, symmetric. What you need is a protocol which is symmetric and distributed, and in the presence of failures, these do not exist. So that's what we use. That's why we use random choice and timing delays, and that's how the protocol works. Okay, so as the device comes into the range, it will choose one of 6524 IP addresses at random, and this is uniformly at random. And then it will send a probe which will query if this address is in use, and then listen for 2 seconds. And if it has a positive reply, meaning that someone is using that IP address, then it will restart the protocol. Okay, so it will go to the beginning of the protocol. And otherwise, it will continue sending probes and listening, okay, for 2 seconds. These are parameters that are taken from the standard. Now, after k probes sent with no reply, it will start using the IP address. Now there is a little bit sort of at the end, but that's a technicality. So it will try to assert it. Okay? Now the question is, what do you think? Will it work? I mean, chances are that you might be running it on your... if you have an Apple wireless network at home, you might be running it. Will it work? Well, a possible problem is that the number chosen may already be in use, but because we are working in a wireless network, there are lots of failures in that network. What if the probes get lost or delayed? So it is, quite likely that the device will start using the IP number when another device is using that.
Yeah, I was just going to say, it seems likely that there's a hardcore upper bound of how many distinct devices you can profitably run this on. 65,000 is not that big a number.
Right, but 65,000, this is the number that's allocated within the IPv4. Yeah. So this is a limit that's specified by the IPv4, and I imagine in IPv6 it would have more. But anyway, 65,000, even if you sort of imagine a truly ubiquitous scenario, that's probably still quite a lot, I think, to choose from.
But there are actually 2 part 32
Sorry?
IP addresses. There are actually 2 part 32 IP addresses.
2 points?
2 to 32.
Right, in IPv6.
IPv4.
No, IPv4. Well, but these are the numbers that are allocated by DHCP. Okay, so this is the range that's taken from the standard. It's the range that DHCP allocates, and this protocol is allocating in the same range, but in a different fashion. So, okay, so the probes may get, so of course the issues are, well, we know that you can send more probes, but then you wait longer, and why would you want to wait for 8 seconds to configure your PDA? And there is no justification for these parameters in the standard. I mean, they actually said, if your network is slow, then use this value. If it is a reliable network, then you use a different value. So, of course, what we want to do is we want to do an analysis, and we used a particular model. We used the Probabilistic Timed Automata model, and I'll skip over that. And we used the cost time analysis, and, I mean, bingo, that's what you have. So with this type of analysis, we've looked at the different number of hosts. We have applied abstraction here, okay? But for a different number of hosts, you can see the sort of unpleasant trade-off. Now, the idea is that this is a problem where you just have trade-offs. So basically, you can't do any more with this, depending on the parameters, depending on the properties of your network. But perhaps what you might want to have is, if you are configuring a network at home for this, maybe you want a web server where you specify these things, and then out, comes up with the best parameters for your particular network. So I think that's the issue here. Okay, now the Bluetooth. The Bluetooth protocol is is different. So I assume that everybody here has got a Bluetooth-enabled phone. Yeah, well, probably almost. Okay, so Bluetooth is a standard which is now into version 1.2, and it is widely available. Now, what Bluetooth uses is, because it runs in the unregulated frequency, and I'm not joking, unregulated frequency, meaning that your microwave is running on the same frequency as well, and that means that the Bluetooth device can interfere with the microwave. And I've given this talk at Stanford, and John Mitchell says, I have a friend who has a Bluetooth phone, and every time he switches on the microwave, the phone stops working. So it's a very real thing. Okay, so the way to resolve it is that Bluetooth communications are actually done through a very fast hopping according to a pseudo-random frequency. And I'll show you, you see how this works. So the inquirer will hop faster, but as you can imagine, in order for two devices to communicate, they have to physically meet on the same frequency. So that's what we did is we looked just at the device discovery phase. Okay, so a device is in a standby, and we only looked at one master and one slave. And the master is the one that will initiate a search for any devices in the range. So we've looked at basically this kind of phase. Well, this is a very important phase because it is essential. No communication can start, and it uses a lot of energy. So that's why it is an important thing to look for. Okay. Now this is how frequency hopping works, and I have to say that when I was writing this proposal, I looked at the protocol. I looked at some papers of the protocol, and I didn't realize how complex this protocol was. It turns out that every Bluetooth device has a free-running 28-bit clock, which ticks every 312 microseconds. Okay? Now, the master will broadcast inquiry packets on 2 consecutive frequencies, and these consecutive frequencies come from some range, and then it will listen on the same 2 plus some margin. Okay? So the important thing is that each of these devices can start with the clock being in any value. Okay? That's a huge number of potential infinite states. Now, the frequency sequence, it has to be reproducible, it has to be pseudo-random because they have to meet, is determined by this. And I suppose I've seen this, but I didn't think much about it until the postdoc started working on that. And this is actually what the sequence is. And as you can see, well, these are called trains. Each line is called a train. And as you can see, in the second line, there is no 1. Okay, and 1 then comes back later. So in order to model this protocol at that level of detail, we had to take account of this. And we also had to take account of the number of possible initial states. And that's what limited us to just 2 devices, because 28 bits of a free-running clock is quite a lot of states.
Could you tell me again? What is each line doing here?
Well, okay,
and
so
why is it the case that they come in almost pairs?
They come in almost. I don't know. You see, this is
I mean, it's sort
what
of
an engineer has obviously produced. I cannot.
Okay.
I cannot. But you know, the idea is that each. So these are frequencies. So the whole range is divided into frequencies. And the device will hop around these frequencies. So for example, if it will start here, then it will listen on these 2, okay? And then it will move on listening on these 2, and so on, until it hears from the other one at the correct frequency. So everything here has to eventually repeat. The whole sequence determines on which frequency each of the devices listens and then also sends an answer. But just to show you a real example of randomization, okay? So both devices will hop around these frequencies, okay? But you can imagine if you have a single master and you have 2 slaves, then it is possible that both slaves will try to reply at the same frequency. And in order to avoid that, they use a randomization, and randomization chooses a delay at random, okay? So it chooses a delay in this range at random in order to resolve the possible conflict. And, okay, so what did we get? Well, this was a very complex interaction. And probabilistic modeling was really essential for 2 reasons. Because of the pseudo-random frequency and also because of the random delay. And the model was so huge that there were 17,000 million of possible initial states. But I mean, you can imagine these days, if we are all going to be instrumented with modes, this is a possible, ubiquitous computing scenario. So perhaps we should be looking at these problems. Now, of course, why not use simulation? Well, I mean, well, others have tried, but can you imagine running 17,000 million of simulation runs? You'll never get, the result. You only get approximate results. Okay. Now, in our case, what we could obtain is actually the best and the worst case time to hear, one message. But there is more. We've also discovered incorrect probabilistic assumptions in other people's models, and I'll show you, on a plot. Now, if you want to know, has anyone any guesses what the worst case time for a Bluetooth device to hear one message is? Well, I'll show you in a minute, and we can actually pinpoint a precise sequence of frequencies which would lead to that.
So can I ask that? So the 17,000 million states.
Yeah.
You don't know how to deal with that, but I understand what you're saying is that if you look at specific questions, you can answer them, namely the best worst case questions, because presumably they allow you to select a small subset of the initial states. Is that why? Or?
No, that's because of the way this analysis works. But I can also look at averaged, because I can
But you're not churning 17,000.
force randomization
right.
onto the 17,000 million initial states. So I can also look at these.
But you're not churning through 17,000 million initial states when you do this analysis, are you?
We are.
You are?
Yeah,
okay.
but yes.
It just so
in
happens.
32 separate model checking cases, because we work backwards, and for that property we could actually divide it and put it together.
I see.
Yeah. Yeah. I mean, anything else would have been an approximation, which is what other people have done. So this was the first sort of detailed thing. So, I mean, we 32 cases. There were actually sort of various manual abstractions that we had to, property preserving abstractions. Now, we've looked at the two versions, and we can confirm why they modified the protocol, because it was the version 1.2 is faster now. And we can also get a power consumption analysis, but that's not too difficult, because that depends on the time. So here I'll just show you a little bit of why this type of analysis differs from simulation. Okay, so the 17,000 initial states, are now plotted, and this is the time to hear a reply. And it's interesting, you have these sorts of peaks. I mean, of course, these are sort of plotted according to now each peak looks like that. And this is the worst case time to hear one message, 2.5 seconds, as opposed to 635 microseconds, because of course it could be lucky, so you could hear it after the first attempt, okay? So this is just a representation, you see, cumulative representation. So because the model was so huge, we thought, well, at least it's a start. We have a time to hear one message. How about we can now combine the time to hear one message with the time to hear one message? We get time to hear 2 messages. And this is what we did, okay? But what you see here in blue is the time to hear 2 messages, which is calculated exactly from a model. We managed to build a model for this, okay? Which was larger, of course. And from that example, you can see that this is the exact, and this is what you obtain from convolution of 2 distributions. One, each represents the time to hear one message. So basically, the upshot of this is that this assumes probabilistic independence, which is actually not in the model. Okay, the model has some kind of, so these are the corner cases of probabilistic model checking. Okay, cases like this.
So was the protocol developed sort of experimentally?
I imagine so. Yes. I don't really know.
Fixing values like 520 microseconds must be.
So of the papers that we've seen, see, if there was a paper that tried to look at the protocol at that level, they said, I'm just going to assume that it starts in such and such a state, okay? or I'm going to run a simulation, or I'm going to assume, I'm going to ignore the pseudo-random frequency. So they cannot get, these values. I mean, in a simulation, whatever you do, you've always get averaged results. So, for example, I could always put a probability distribution on those 17,000 million, and what you get is something which will be in between the worst and best case. So that's the Bluetooth example, and I don't have time for the FireWire, protocol. So I'll just finish off if I can find the right one. No? Ah. Sorry, no, it's okay. Right, so there are a number of related projects, and in particular, I think what we are talking to Andre about is modeling biological processes, and this is because probability features in a big way, and there are some projects that are starting out in there. And okay, what we're also working on is extending the PRISM modeling language with mobility, so that we can model genuinely mobile scenarios. Because even though I've showed you examples, real-world protocols which are used in ad hoc protocol setting, I have not used any of the mobility features. We always looked at some static configuration of nodes. And, well, there are a number of challenges, you see, for future. And the biggest one is going to be combining this with some kind of compositionality, decompositionality, approximation methods. I think some progress has been made in that with the sort of simulation and statistical-based approaches. And finally, well, real software, not models. I think ideally you would like to work with something like C and with whatever libraries. So in due course, maybe. Now, if you are interested, then the set of case studies and, model statistics, etc., they are all on the PRISM web page, and that's the link to the PRISM web page. And this is the list of collaborators, people who are using PRISM, either contributing to code or models, or, we are working with them on connecting the tools. And here are some names, to acknowledge. So it has been quite a large project with various contributions. Okay, thank you.
Any more questions? Thank the speaker.
So given a model, probabilistic model, you're able to make worst case and best case bounds, probabilistic bound on certain behaviors.
Yes, we can calculate the worst case, best case probability. Yeah.
In general, that seems like a very hard problem. To do this. But let's say, suppose I give you a randomized algorithm.
Yeah.
People spend a lot of time trying to prove that those algorithms actually work within an error bound. Right. So why is that? Or can we actually use this for proving bounds for any randomized algorithm?
I would have thought so. Of course, you will be limited by regularity and model size. So whether the model can actually be constructed. But if you are telling me, well, I've got a randomized algorithm, then I imagine that randomized algorithm is going to be a discrete time Markov chain. Of course, the first hurdle will be, is it going to be finite state? Because at the moment, that's the only discrete time Markov chains that we can handle.
So what's the size of the state space you can deal with right now?
Well, for some, for some we can deal with absolutely ridiculous. I mean, 10 to the 30. Yes, we've done for some randomized distributed algorithms. We tend to do better with Markov decision process models that come from randomized distributed algorithms, because these have randomization. They only have very few distinct probability values. For continuous time Markov chains, which I really didn't cover because they don't really play a major part in ad hoc network protocols. Well, for these, I think we are, yes, by a factor of 10, I think, smaller, because numerically the calculations are a lot more involved, and you get what is known as stiff Markov chains, where you can get a whole range of different probability values. Yeah. Yeah. Now, people have done some, yes, there are quite a lot of interesting examples on the PRISM webpage where people have sort of contributed. There is a futures market investor, there is a negotiation which has been recently contributed from Liverpool. I think, I'm not sure whether that's on the webpage, but even a sort of random graph creation and checking of these bounds, yes. But, I mean, I caution you, I mean, because the algorithms are iterative, then we work with something like accuracy of, say, 10 to the minus 6, and whether this is good enough, for, yeah.